I'm going to start recording. So the plan for today is to talk about, so I want to discuss returns to scale from an average cost point of view. I know that we talked about returns to scale in terms of the production function. So this is a little bit different, but the concepts still kind of remain the same. And then from there, I'm going to talk about optimal labor and capital inputs when we have an unconstrained level of quantity. So just kind of a reminder, when we were talking about like cost minimization, for example, that was under the context of a set level of Q or Y, right, where we already determined how much the firm was going to produce. In this case, we're going to say that we don't know how much we're going to produce, and we don't know how much of each input we're going to use, but we're going to use certain conditions in order to maximize the amount of profit that we come up with, which is, as you guys are probably familiar with, revenue minus cost. So with that being said, I wanted to talk about returns to scale. And I'll try to make this as quick as possible, just because I think that the bulk of the material that you guys are going to be interested in is first order conditions and just general cost curves. And I'm sure that you guys have seen like problem set 9, problem set 10. There's a lot of these quick questions where it's like, how much is the firm producing? And we're going to get into all that today. So getting back to this, returns to scale through average cost, okay? And so we know that average cost is going to be a function of the inputs and however much we're producing. So this is the cost of the inputs, right? Because this determines how much everything costs. So, right, we're very dependent on what these two inputs are. And so we know that average cost is pretty much just total cost. So cost as a function of, I guess, cost would be the function of all of these, but I'm just going to leave it as just cost as a function of how much we produce. And we're going to say that this is divided by however much we actually do produce, right? So total cost, right? So just for shorthand, so total cost over quantity. Maybe this is a format in which you've seen it before and it's more comfortable to you guys, right? And so hopefully that makes sense. It should be pretty intuitive, this equation. And so the way that we're going to determine returns to scale is through two different levels of production, right? And so we're going to denote that Y star, this is the original amount of production, and this is Y double star, which is how much we produce when we scale up, pretty much. And so I like to think of Y double star just being equal to 2 times Y star. I think that conceptualizing it in terms of just a 2, I think that's the easiest way to kind of work with the numbers. But again, Y double star can be any constant that's greater than 1 times the original amount of production, okay? So that's kind of just the importance there. So let's get into how we're going to work with this. So we have certain, I guess, I'm going to list out basically the information that is important to you, and then I'm going to explain why it is that this is true. So when we have that average cost, and I'm just going to denote this by the Y star, but just remember that it is dependent on these cost inputs. We're going to say that when the average cost of producing the original amount is equal to the average cost of producing the scaled up amount, that this is constant, right? And it probably makes sense. I think whenever you can see an equal sign, it's constant. This is kind of like the easy like gimme. It's when we have the different signs that it can be a little bit tricky. So I'm going to just kind of talk about this, and then I'm going to get into decreasing, and I'm going to get into increasing. So we know that this equation is essentially just cost of Y star over y star, right? And we say that this is equal to the cost of y double star divided by y double star, right? And if you guys can imagine, let's say that, so we're going to say that we let y double star be equal to 2 times y star, right? Just for the sake of this problem. We're going to say that when we double however much we produce, that's kind of, and I hopefully this makes sense to you guys. When we double how much we produce, that's going to double, or it should kind of double how much cost that we have, right? So that's kind of the intuition there. And so essentially what we're saying is when I double my quantity produced, I should theoretically be doubling my cost. And so this, right, is, let's think of y star as being 1. So let's just say that we originally were producing 1 unit for $10. So this was 10, right? Basically, our cost should double, right? Because we know that y double star is just going to be equal to 2. And so in order for this to be true, we know that this essentially has to be equal to $20, right? Where our costs are doubling as well, okay, when we double our inputs, right? So that's kind of like what you would expect to happen. But we know that in this class, right, with various production functions, that's not always going to be true, okay? That's just kind of like the baseline in which we're going to assume that that's going to happen, right? But as I mentioned before, that's not always going to happen, okay? But we know that basically this is true, and I think that this will probably be the easiest one for you guys, just because this equal sign typically denotes constant returns, okay? So let's get into kind of the trickier ones. So we're going to say that when the average cost of y star is less than the average cost of y double star, right? We're going to say that we have decreasing returns to scale. Okay? And so why is it that we have this? Well, we know that essentially we are kind of thinking through it like in a point of view of, well, how does doubling our production, right, affect our costs? Okay, and so we want to think about it in terms of this, right, where we know that this is always going to be true, right? This equation is always going to be equal to this inequality, right? Or I guess this fraction is what I meant to say. So you have something that looks like this. When I double my inputs, or when I double my production, I should say, right? If we think about y star as being 1, or I guess y double star as being, so let's just let y star equal 1, and so y double star is equal to 2, for example, right? So we can kind of just fill in these denominators because this is just like an identity, right? And so essentially, we know that in order for this inequality to be true, that the costs, right, of producing twice as much, right, are more than doubling, right? So this basically has to be twice as much as this, right? And so if you want to think about it as when you, so just for example, right, this is, say, 2.2, just theoretically. So this is like 2.2, okay? Think about it when in terms of normalizing your costs, right? So if you think back to the production function, right, we said that we had decreasing returns to scale when doubling our costs less than doubled our production, right? Meaning that if we think about this ratio in terms of the production function, right? Doubling our cost would be akin to saying 2 times this production function, right? So essentially, when we double our inputs, and I'm referring to the production function here, when we double our inputs, we got less than twice as much production. Well, think about this kind of fraction that I have here. I have cost over production, and so decreasing returns to scale resulted in a cost over production ratio that was less than 1, right? Where we essentially, or I guess more than 1, I should say, right? Where we doubled our cost, but we less than doubled our production. This ratio is still true, right? Where we've 2.2 times our cost and we've doubled our production, and you can see that this ratio is greater than 1, right? So I know that this is maybe a little bit harder to follow. I think that returns to scale through the production function is a lot easier to kind of see. But I hope that you guys are able to kind of realize the pattern that I'm kind of producing, where with the production function, right, I essentially doubled, so 2 times cost, and I less than 2 times, so this is a less than, I less than 2 times production, right? And so this results in an inequality, so cost over production, that's greater than 1, okay? And so this is kind of what I've just reproduced, just in a different lens, okay? So kind of think of that. And so hopefully that is, you can kind of see the connection between returns to scale through average cost and returns to scale through the production function. If you don't, I think that that's all right. Just kind of think about what these inequalities mean. And hopefully it'll kind of come to you guys. The last one kind of follows the same exact reasoning. So the last one is saying that if my average cost is higher when I'm producing less units than when I'm producing more units, then I have increasing returns to scale. Right? And to kind of put this into perspective, right, having a high average cost is just bad in general, right? We would prefer our average cost to be lower. And so when we produce more and our average cost is lower, that should mean a good thing, right? So if you don't really like the mathematical approach to it, I think thinking through this line should kind of help you guys think about it in a more conceptual light, right? Where essentially you want to have lower average costs when you produce more. And we know that increasing returns to scale is better than decreasing returns to scale. So maybe that's something like a connection that you guys can make. But in terms of the mathematical approach, and this will probably be the last that I talk about, returns to scale through average cost. But essentially, we know that I've doubled my production, but my costs have less than doubled, right? And you can kind of think about how this ratio right here is less than 1, right? This is 0.9, so less than 1. And we know that with increasing returns to scale, when I doubled my inputs, I more than doubled my production, which means that my cost over production for the returns to scale through the production function was less than 1, right? My cost over production was less than 1. And it kind of is the same exact concept here, right? Where 1.8 is kind of just arbitrary. It's just something that's less than 2. But hopefully it kind of shows to you guys what I mean. So are there any questions about this? Feel free to leave them in the chat if you do. I know that this can be a little bit tricky to kind of think about, just because, well, I'd say that the other method of returns to scale is easier. but they might not necessarily give you a production function, and they'll just say, these are the costs, this is how much you produce, what kind of returns to scale do we have? And so this is how you would think through it, all right? And I'm guessing that there's no questions about this, and so I'm going to go ahead and move on. So let's see. I want to talk about now the profit maximizing kind of steps that we're going to take in order to solve unconstrained quantity problems. So I want to first kind of talk about a problem that is in the short run, and then we're going to then talk about in the long run kind of how we would solve this exact same problem, right? So this is problem set 9, question 3. I'm sure that you guys have already kind of looked at it, or if not, this will probably be a good just general question to think about. And we're given a production function that is 4L to the 1/4 K to the 1/2, right? And we're asked to find labor in the short run, given these kind of parameters, right? Where we have quantity, wage rate, rental rate, and a fixed level of capital, right? And we know that in the short run, we're always going to have fixed capital. And that's kind of one of the defining characteristics of the short run is we have these fixed costs, right? And in this case, capital is fixed. So we want to say, how do we look at this and determine how much labor is going to be the optimal amount? Well, so we're not given any numbers, so it's gonna be left in a very general form that you'll later be able to plug in values into that. It's kind of like a demand function where the demand function takes in any given prices and income, and it spits out a number. It'll be very similar to this, right? So how do we kind of go about this? Well, first off, we can say that this is fixed, and we also know that this is equal to quantity. We don't know what quantity is, but it's important to have quantity just kind of here as like a placeholder. And you'll see because we're going to be able to kind of work with this variable as well. And so given that we can work with this variable right here, I think that it's a good idea to isolate L by itself, and then kind of we can move forward through there, right? So instead of working with our profit model, which I'm going to remind you guys of very briefly, instead of working with our profit model, we're going to be working through the production function. And this is something that you'll notice we do a lot more of in this material than in material past, where a lot of our stuff was working with a budget constraint. This is going to be, so we were working a lot with the budget constraint and not so much with the utility function, right? This is going to be a lot more emphasized on working straight through this production function up top. So kind of to stop rambling on, I want to isolate L right here, right? Because this will be in terms of some of the parameters that I've been given, right? So we know that L to the 1/4 is going to be equal to Q over 4 K bar to the 1/2. And so L is equal to Q to the 4th times 4 to the 4th K bar squared, okay? And so this doesn't necessarily tell us, right, kind of what our optimal levels of labor is, because we don't know what the level of quantity is as well, right? We basically have two unknown variables, L and Q. So hypothetically, if we were given a Q, it would just be as simple as plugging in Q and plugging in our value for K bar, which will almost always be given, I think. And so, yeah, that's kind of the intuition there. But we have what our level of L is, but this doesn't spit out a number just quite yet, right? Which is why we need to work with the profit equation. So let's kind of divide this. So we know that profit is equal to price times quantity minus total cost, right? Where this is our revenue, rev, and this is our cost, right? And at its most basic level, this is what profit is, right? In the real world, we have a bunch of like taxes, administrative costs. I'm sure for all of you like accounting students, you guys probably know this a lot better than I do, right? But profit in like the real world isn't broken down into simple revenue and costs, but in this model, we're going to assume that this is all that goes into profit. We also know that quantity, right, is a function of our labor and capital inputs, right? Which means that Q is not a static number, right? We can't just work with Q as it is. We need to kind of work with the production function that we're given. So this is equal to P times FLK. And our total cost, right, is broken down into also two components. It's broken down into, we're just going to use L and K right here. So WL plus RK, right? This is how much we spend on costs. And just kind of be familiar that when we eventually expand this equation, this negative is going to be distributed here. But yeah, so that's kind of what we have to work with so far. And so we want to find what the profit maximizing level of labor is. And so how we do this, right? So profit is here, and we're looking for the profit maximizing level of labor. Well, we know that at a profit max, that the derivative of profit is equal to 0, right? And so if we're finding an optimal amount of labor, we basically want to take it with respect to labor, right? You see how we are taking it with respect to labor. And what this tells us is that basically we want to be at a point where increasing our labor by 1 unit is not going to affect my profit, right? Basically, we want to be at a point where if we increase our labor by 1 unit, then we lose profit. And if we decrease our labor by 1 unit, we also decrease profit, right? We want to be at that point where profit is steady, okay? That's why we set it equal to 0. And so if I evaluate this whole equation with respect to L, right, I get something that looks like this, right? P is going to be a constant, and I know that my production function is has inputs L, which means that we need to take the derivative of this with respect to L. So this is the derivative of the production function with respect to labor, and I'm just going to distribute this negative right here. RK doesn't have an L term, which means that it's just a constant, and so it'll evaluate out to 0. But we have a WL right here, and so the constant in front of L is W, which is why we are left with this minus W. And if you guys remember from, I can't remember, it must have been 2 weeks ago, probably 2 weeks ago. If we remember, this equation right here is the marginal production of labor, right? Where we see how much increasing 1 unit of labor affects my production, okay? So this, when I kind of just move W to the left side, is equal to P times MPL. And this is what we call our first order condition. You'll notice that I can do the exact same thing with respect to capital, and that'll kind of give me this equation, except that it'll be R and P times MPK, right? But the concepts are pretty much the same. And before I move forward with the problem, I want to read you guys out this equation and kind of walk you guys through why it is that we are at this level, okay? So P, right, is how much we can, let me make sure that this is inside the screen. P, right, is how much we can sell the products for. P in a market is just given, right? Where a single firm can't change the price, right? So they take price as given. And this is something that you've probably learned in like Econ 1 or just any introductory econ class. In a large market, price is just given to us, okay? So we have no kind of effect on what P is. And so as a result, P is how much we can sell our product for. Marginal product of labor is the increase in production that hiring one more unit of labor brings you. And so if you think about it, MPL is just some value of quantity, right? And so P times Q, right, some value of quantity, is equal to the additional revenue that bringing one unit of labor in, right, brings us. And so I basically want to be at the point where this is equal to the wage, right? Because the wage is the cost of bringing one more unit of labor in, and P times MPL is the revenue of bringing one more unit of labor in, right? And so if you kind of think about it just from a conceptual point of view, if we're paying a worker more than the revenue that they're going to bring in, we're losing profits, right? And likewise, if we're paying workers less than the revenue that they bring in, we could gain more profit by hiring more workers, right? Because each of those workers is going to keep bringing in a positive profit up until that worker that brings in no profit, and then that's when we stop hiring, right? So this is kind of the intuition behind these equations, and I want this to make sense to you guys because this is this is going to be like the keystone of a lot of these problems that you're going to be seeing from now on, and you probably already have seen. So let's kind of circle back to the original problem that I had, right? So I'm going to erase this and kind of keep moving on with this problem just on this side of the board. So this is kind of like a general demand for labor, right? But it requires us to know the value of quantity, okay? I'm going to basically create a value for labor that is independent of the amount of quantity, and so therefore tells us how much labor we want without having to know how much quantity we produce, okay? So let's kind of go back to this P times MPL equals to W equation, right? Because this is how much labor we're going to want to bring in. And so let's work with this kind of equation for now, right? And see what this brings us. So P times marginal product of labor, I'm going to be taking the derivative of this with respect to L. And so I'm just going to do this real quickly. But this is L to the negative 3/4 times K bar to the 1/2, right? And this is going to be equal to W, right? I'm going to, what am I going to do? I'm going to move this to this side and move this to this side, okay? So I have P times K bar to the 1/2 over W is equal to L to the 3/4. And so basically my optimal level of labor is going to be equal to this whole term, P times K bar to the 1/2 over W to the 4/3. And this probably isn't a very exciting problem for you guys because you don't actually get to see a number being produced. However, what you'll notice between this and this is that we no longer have any unknown variables, right? Because P is going to be given, W is going to be given, and K bar is going to be given, right? So we automatically know how much labor is going to be the perfect amount based on just based on this equation right here. And so if you want to find out how much quantity you're going to be able to produce, well, we know what L star is, right? This is a number. So we plug this value into here. And we also know what K bar is. And so this is just our production function, and it's going to spit out a quantity, okay? So very important identity. You definitely need to know this, okay? Working with another problem, um, remember, this was in the short run where we had a fixed level of capital. Let's look at a problem in which we don't have any kind of restrictions on capital. And so L and K are both unconstrained, okay? So this is problem set 10, question 1. And we're given that F LK is equal to L to the 1/2 plus K to the 1/2. And I like setting this equal to Q right away, just in case we want to work with it. So that's just kind of like a tip from me to you. I don't think it's necessarily always going to be necessary, but I think that it's a good habit. And so we're given information such as, we're not given Q, we're given W equals 4, R equals 1, and P equals 16. And so so kind of to talk about this in general, you're basically always going to be given this information. I think that the only time in which you would not be given this information is if you're like forced to work backwards to find it, where you're already given a like production function and you've already determined what the optimal level of L and K are, and you need to work backwards in order to figure out what these variables are. But that's like the only instance in which I think you would be like required to know this. So for example, if I had L star is equal to P R W squared, right? For example, and this is all just kind of arbitrary. If this was my demand for labor and I already knew how much L was, then I would just set this equal to, I don't know, 15 and kind of solve variables from there. And I know we have a bunch of basically unidentified variables, so we wouldn't be able to solve it straight through there. But I'm guessing we would be given a situation in which we only have one unknown variable, and that's kind of like, it'd be solving for that. But every other instance I can think of, you're going to be given this information, right? And so we're asked, what is L star and K star, right? So this is the optimal level of labor and capital in the long run, right? Because they're both unconstrained, okay? So in a case where they're both unconstrained, right, you kind of think back to our like utility maximization like days, right, where we didn't know what x1 and x2 were. And so we basically had to find an optimal, like a utility optimizing maximum point, right, which was like a point of tangency, or it was a point on the extremes. So
Eric, real quick.
Yeah, what's up?
When they asked us to find L star and K star, but we kind of have two different types of L star and K star in these type of functions, right? Like we have one for maximizing production and maximizing profits, and one for minimizing costs. They have different arguments in them, right?
Well, yeah, because so they have different arguments. I think it'll be pretty obvious as to like the difference between them and like ultimately what you're going to be required to find. In this situation where Q is not known, it's a very different process than when Q is known, because when Q is known, you just find the TRS, set it to the cost ratio, and you plug it back into the production function. It's a little bit different here because we're now going to be using our first order conditions. But I believe that the arguments are going to be different. And so for those who maybe don't know what arguments is, arguments are like the parameters. L and K in this instance are arguments, okay? And so, yeah, it'll be different, but not like wildly different. So we want to find what L star and K star are. And you'll notice that the first step, right, is maybe intuitively to find our first order condition. So I'm going to start off with that, and I'm going to show you why maybe that's not the best first step. I mean, having that information down already is definitely important, but I'm going to show you how when we start off with the first order condition, we're going to have to end up circling back at some point. Okay, so let's look at our first order condition, and let's look at P times MPL is equal to W, right? So P times MPL is actually, luckily, we only have L in terms like in here. So this is 1/2 L to the negative 1/2, right, is equal to W. And so we've actually gotten pretty lucky where K is just treated as a constant, but you can imagine how, and I'm just going to kind of show this as a counterexample. You can kind of see how if we had a Cobb-Douglas equation, finding P times MPL equals W would return something that has L and K within my marginal product of labor, right? Where this would be equal to 1/2 L to the negative 1/2 K to the 1/2, right? And this doesn't tell us any information because we still have two unknown variables inside an equation, and so we can't really work from here, right? But you'll notice how essentially in this case we actually are able to do that. So when I solved this problem on my notes, I found the TRS first, but I'm actually very curious as to see whether you can basically just solve for L straight away. So let's kind of see how that works out. So this would be P over 2 times the square root of L is equal to W. And so I'm just going to solve for L. So square root of L is equal to P over 2W. And so L is equal to P over 2W squared, right? This is equal to 16 over 8 squared, which is equal to 4, right? So you actually are able to determine L right away from this kind of general setup, and you don't need to find your TRS first, right? So this is a situation in which you are able to do that, but I wouldn't recommend starting with the first order condition. I didn't realize that I kind of got lucky when selecting this problem. But a more general approach, and I think that this is the approach that you guys should kind of bring to every single question, is finding the TRS first. So I think step one is find the TRS and see if you can set this equal to your cost ratio, which is W over R, right? So this ends up being, let's see, 1 over 2 times the square root of L over 1 times 2 square root of K, right? And this is equivalent to K over L, right, after simplification. So you'll see that we do have diminishing TRS, which allows us to set this equal to our cost ratio, which is W over R, which is just 4. And I think that the reason I would definitely approach it in this way, even though I just showed that it's possible to solve it just through the first order condition in some cases, is because typically, like the most popular production function is a Cobb-Douglas production function. And you need to go through this step in order to finish these Cobb-Douglas productions. So I think that going through this extra step just prepares us for any kind of question that's given to us, right? And so we're given that K star is equal to 4 times L star, right? So at our profit maximizing levels of capital and labor, we're going to have 4 times as much capital as we do labor, okay? And so here, hold on just a sec. Yeah, 4 times labor. And so when I look at this, right? So square root of L. Actually, I'm gonna leave it as this for now. I kind of prematurely squared it, and I'm not sure if I can do that yet. But either way, we have diminishing technical rate of substitution. And so I'm going to leave it as a 16 for now, but this might change if I think that it's not 16 times L. So kind of just take this with a grain of salt just for now. But it's either 4 times L or 16 times L. It all depends on whether I'm able to square this whole thing or not. So let's look at kind of what we have so far, right? We have that we can now use our first order conditions because we have variables in terms of the other, meaning that when I get to that point where like I do have my like first order condition in terms of 2 different variables, I'm able to plug these values into there, right? If that makes sense. So I know that this example in retrospect isn't necessarily the best kind of to show this reasoning, but I want you to think about it in terms of a Cobb-Douglas, how knowing what one variable is in terms of the other allows us to kind of correct for the fact that our first order condition is in terms of 2 unknown variables. In this case, our first order conditions are not going to be in terms of 2 variables, meaning that we can solve for optimal values right away. But just generally speaking, this is kind of what's going to having this step allow us to kind of move forward through here. So let's use our first order condition. So we've already solved for L star, and so I'm just going to kind of leave it as that. And so L star, remember, was 4, but I want to see now whether our TRS, right, kind of holds in that we would expect K star to be 64 or 16. It's one of the two. It kind of just depends on whether this is K over L or if it's square root of K over square root of L. So yeah. So we use our first order condition for P times MPK equals to R. And so we have that P times 1 over 2 square root of K is equal to 1. And so P is 16. Okay. And so let's kind of work through here. 8 over the square root of K is equal to 1. And so 8 is equal to the square root of K, meaning that K is equal to 64. Okay. So this is true where K is 16 times L. And so essentially,
can you move the camera up a little bit? Thank you.
Yeah. Kind of what I wanted to show right here, and this is kind of a sidetrack from the main kind of goal of the problem, is that when you have your TRS, right, I wouldn't square it. So I would leave it as something like this, right, where even though this is the same as K over L, it has the possibility of messing up our TRS to cost ratio kind of equality equation that we have. So leave it in terms of this, right? Because we found through the first order condition that we do need to leave it as this. And so these are kind of the general steps in which you want to approach this. It's a lot easier to show with a Cobb-Douglas equation, right? And actually, let's go ahead and do that just because we do have some time. Let's show this is L to the 1/2, K to the 1/2, right? And so it'll probably be a little bit more evident as to why we need to do something like this. So we have that TRS, this is just going to be K over L, just straight up. And so this is equal to W over R, which is equal to 4. And so K is equal to 4L, right? And so when we look at our step 2, which is the first order condition, we have that P times MPL is equal to the wage. So P times 1/2 K to the negative 1/2 K to the 1/2 is equal to W. And I'm just going to plug in K into here, so 4L. And so I get that, let's clean up this equation for now. So P is 16, K to the 1/2 over 2 times the square root. Oh, this should be L. I apologize. This is L, and this is the square root of L is equal to W, right? You notice how in this scenario, we have 2 unknown variables, which kind of screws us. But luckily, we can substitute this value in and get 4 times L in this scenario, right? And be able to work through here, right? So this simplifies out to 16 times 2 square root of L over 2 square root of L, right? This is equal to the wage, right? And so from here, the wage is 4. Did I do something wrong? 2 square root of L, K to the 1/2, 4L to the 1/2. So 4. So this should be equal to 8 square root of L, 16 times 4L to the 1/2, right? Either way, I think that you're going to be able to determine a level of L, right? Just through algebra. And so let me kind of just work around through here. We get that 4L to the 1/2 is equal to square root of L over 2. And so 2 times the square root of L. Yeah, I'll send you guys an email, or if you guys have questions about this, I can kind of reconfirm. But more generally, these are the steps in which you take. I think that there must have been some sort of algebraic mistake somewhere along the line. So yeah, that's kind of all I'll say about this. I know that that's like an unsatisfactory answer, but this is like the general step. And I'll take a look at it and figure out where algebraically I kind of went wrong. But either way, right, this is like the general process. And so we do have a little bit of time, and I want to kind of talk about cost curves a bit. And then next Wednesday, we're going to really kind of hammer a lot of the kind of short little questions that you'll see in like the midterms or like the problem sets, where they talk about like what is supply given this like labor function or something like that. So here we are. I want to just generally talk about this cost curve right here. And I'm going to make this very quick, right? Because I know that we're running short on time, right? But this is our average cost. This is our average variable cost, and this is our marginal cost. Drawn to scale, you'll notice that the marginal cost runs through the minimum of our average cost and our average variable costs. This is more of like a 100B kind of question as to why, but it's not something you need to know for this class. The key thing is that this difference right here is our average fixed cost, right? Where if we kind of go back to the drawing board, we see that our total costs are equal to our variable costs plus our fixed costs. And so if we want to get it in terms of average cost, average variable cost, and average fixed cost, we just divide through by Q, right? So that's kind of the reasoning as to why this gap is our fixed cost. So
Eric, real quick.
Yeah, what's up?
Sorry, you said that the difference of average cost and average variable cost is our average fixed cost, right?
Mm-hmm.
Okay, great, thank you.
Yeah, it's this gap that's right here between the two curves. And so what I want to leave you guys with is basically how we're able to kind of determine our production, right? So as I mentioned before, our level of price is fixed in the market, right? Price is given to us, and we have to determine how much quantity we're going to produce, right? And so there's a kind of a key thing that's going to allow us to determine how much quantity to produce, and it's going back to this profit equation, right? That you guys hopefully remember, right? So we have P times, and I'm just going to leave it as Q in this case, and P times Q minus C as a function of Q, right? Where basically however much our cost is dependent on how much we produce, right? And I want to maximize my profits, but in this case, I want to maximize them with respect to quantity, right? Because this will determine how much quantity we produce in order to maximize our profit. So we go to this same kind of setup as our like first order conditions, right? Except that we take it with respect to quantity. And so this Q just kind of, we leave that as just a Q, right? And this will kind of cancel out, if you will, right? Where we're left with P and this right here, C prime as a function of Q. This is our marginal cost, right? Where it's pretty much just the derivative of cost with respect to quantity. So it's how much an additional unit of quantity impacts our cost, right? So this is our marginal cost, right? And this is probably why you've seen the equation that P is equal to marginal cost, right? And so this kind of tells us that we are going to basically always be producing at the point where P is equal to our marginal cost. And so basically if we produce, say, so essentially P is given to us, right, as we've already established, which is why if P is right here, and I'm actually going to make this a little bit lower. If P is right here, then we automatically produce this much because we want it to be at the point where P and our marginal cost kind of curve intersect, and this will tell us how much we produce. Right? This is our profit maximizing level of quantity, right? And so it's not always true that our profits are going to be positive. There's cases in which profits are negative, but that's something that I'm going to talk about on Wednesday, as well as go over hopefully a lot of practice problems just to get you guys ready for your final. So I know that we kind of covered a lot of material today. And so if you guys have any questions, you guys are more than free to ask me, kind of hang around. Otherwise, you guys are good to go, and I'll see you guys either in my drop-in hours or on Wednesday. But yeah, definitely feel free to ask questions and kind of just, yeah, just I guess ask questions or.
Eric, real quick. So like if they told me to find the optimal amount of Q that I need for a certain price, I would just take the marginal cost, set it equal to the price I was given, and solve for Q. Would that be?
So yeah, basically through this cost curve, we know that whatever the price is, which is given, we want it to intersect with our marginal cost. And then when we go straight down, that's going to be however much quantity we produce. So yeah. And I'm sure there's a way of deriving Q, but I don't have enough time to get into that. That's kind of the intuition behind that. Let's see, was there a question? What happens at the point Q prime comma P? So this is basically the point in which you're maximizing profits to the best you possibly can as an individual firm. And why is it equal to 0? Oh, this equation right here, it's equal to 0 because you basically want to get to the point of quantity where the change in profits is 0, where basically you can't have any higher profits. Does that make sense? Yeah. All right, and yeah, awesome. I'm glad that it makes sense. And I'm gonna move it to my drop-in. So if you want to see me there, great. Otherwise, have a nice day.